All right, back from break. So we took a good thorough look at frictional forces in the first part of the class today. And now we've moved on into a uniform circular motion. And we just got through showing that if I have something in circular motion, the accelerations are towards the center. So let's take a look at some examples and kind of get an intuition for why that would be the case. Let's say that we have an object, it's a 150 gram object, and it's on the end of a string, and it's in a horizontal circle. So, it's like rotating this around my head or something. In any case, this is a top view looking down, so it's not going vertically where the speed might change. It would be harder to keep the speed uniform. This one's going at a uniform speed. It's in a horizontal plane. It's a 150 gram ball, an object. It's revolving uniformly in a horizontal circle with a radius. Now notice, that's a radius, not a diameter. The radius is 60 centimeters, and the ball makes 2 revolutions every second. So that's pretty good speed, right? 1, 2, am I counting right? Let's see. 1, 2, something like that. So, and it's 60 centimeters for the radius, so it's like a 120 centimeter diameter. So it's, is that fast enough? I think it's faster. So I can't get my arm going fast enough. I have to be able to make 2 complete circles every second from that. So yeah, it's pretty good speed. What's the centripetal acceleration? Now, the centripetal acceleration is it's towards the center. So centripetal, it's just a directional adjective telling us where the acceleration is. So again, the acceleration is going to be towards the center of the circular motion. Here is the mass, or the object, and here is the velocity. Now the mass worked out to be 0.150 kilograms. The radius here is 0.60 meters. And the velocity then, I want to calculate the velocity, it's going to be distance divided by time. Now what they've told us is it's going to do 2 complete circumferences, 2 complete cycles every second. So what we can do is, this is going to be 1 second, that's 2 times 2 pi r. And it turns out this thing's moving at 7.54 meters per second. Now that's, what, 15, 20 miles an hour, something like that. That's a pretty good speed that this thing is moving. And what we had just derived earlier, or with the formula we said we would work from, is that the acceleration can be calculated if we have circular motion. The acceleration can be calculated as v squared over r. So I can put the v values in, square it, divide through by r, check the units. Meters squared here, meters here, one of those meters is gone, and then I'm going to have per second squared. So meters per second squared, this number gets squared, divide by 0.6, that's 94.7 meters per second squared. Okay, and let me mention this too. This acceleration, that's a pretty good acceleration. Right? The acceleration due to the gravitational field of the Earth, 9.8, this is almost 10 times as large. So with circular motion, since the object is staying locally, it's not traveling off to some distant location, you can get some really large accelerations even with the object staying in a relatively compact region of space. Okay, what about this one? This is a little more spread out. This is the moon's centripetal acceleration. So it says that the moon has an orbit. It's almost circular. We can treat it as very closely approximating uniform circular motion. Now the radius, this time, is 384,000 kilometers. And it's a period of 27.3 days. Let's find out what the acceleration is. Now, we probably still want to put everything in terms of meters and seconds. So let's get everything into standard units. The radius then works out to be 3.84, 10 to the 8th meters. Good time to be using scientific notation here. The velocity is going to be a circumference, 2 pi r, divided by the period. Now, the 2 pi r worked out to be 2.41, 10 to the 9th meters. The time, the period, required for one orbit was 27.3 days. So at 27.3 days, I converted that into some number of seconds. So take a look, see if that looks correct. And then taking this number, it says the speed of the moon in its orbit is a little over 1,000 meters per second. So that's fast, right? That's quite a good speed here, 1,000 meters a second. To find out what the acceleration is, we can use the formula we derived, v squared over r. So I put in the, I plug in the v values, I plug in the r values. Now, the distance is really large, so the speed is big, but the size of the circle is enormous. It works out to be a pretty small acceleration, 0.00272 meters per second squared. So it's not huge. Now, where is that acceleration coming from? And it's coming from gravity. So for every acceleration that we see, and we see an acceleration taking place here, there needs to be a force in the direction of acceleration, and that force would be gravity. So here's a good example to think about. If we turned off Earth's gravity, what would happen to the motion of the moon? And if we turned off the gravity, then the moon would begin going in a straight line. Now, what maintains the circular motion? Here is the moon going in a straight line, but it doesn't go in a straight line because Earth is pulling it from the side. So if you pull something from the side, that's going to pull it in that direction. So Earth's gravitation pulling on the moon at each location continues to make the moon redirect itself, and the moon ends up redirecting itself into a circle. Since there's no force speeding it up, no force slowing it down, the force is sideways. So if the force is perpendicular to the motion, that maintains circular motion. And if we go back, we'll see in chapter 6, we'll come back and see how to calculate gravitational fields. What we're going to find out is that that's the value of Earth's gravitational field at the location where the moon is. All right, now here's another example, maybe closer to home, of a centrifuge in a lab. So many of you are probably biological science majors. Maybe you'll be working in biological research labs. Centrifuges are kind of a standard instrument. What you're allowed to do with a centrifuge is take materials and put it inside the tube, and then you spin this thing at extremely high rotational speeds. And what that does is it sets up enormous accelerations. Now that means that the materials inside there will tend to separate by density. The more dense materials will tend to go to the bottom of the tube due to this effect, and the lower density materials will show up in the upper. So you can separate materials by density. If you're looking at some lipids, you're looking at proteins, you're looking at DNA, you're trying to sort out all these different components. And this is one technique for sorting out different components of some biological mix. So here is the ultra centrifuge. It rotates at 50,000 RPM, 50,000 revolutions per minute. A particle, or a part of the sample that you've put in the tube, is at 6 centimeters from the rotational axis. So calculate the acceleration taking place inside here. Now, acceleration creates the same effects as if it were being done by a gravitational field. And so we can measure these in terms of g's. How many g's of acceleration is that? So this is the formula again, v squared over r. Now they've given us r as 6 centimeters. I switched that over 0.060 meters. And then the velocity is 50,000 rotations every minute. So that's the 60 seconds is the 1 minute, and the 2 pi r are the circumferences. And that says that an object located 6 centimeters away from the axis of rotation has a velocity of 314 meters per second. So that thing's going, 600-700 miles an hour. That's pretty good speed. Now that's sideways. The acceleration, which is centripetal, it's towards the center, is given by v squared over r. That worked out to be 1.6 million meters per second squared. So 1.645, I should have rounded back one more. Now, the acceleration can be thought of in terms of some, that's not a normal force, that's just a number. Some number of g's, so the number of g's is equal to a over g. If I take the acceleration that we're seeing with this ultracentrifuge and divide it through by g, I end up with 168,000 g's, okay? Which is, it's a very large acceleration, and so it will be effective at separating out these materials according to their densities. All right, here's another circular motion example. We got a lot of these, so here we go. Let's say that we do have a string. Now is this, again, it should probably be a horizontal, to make this as simple as possible, let's keep this in a horizontal plane. Now, there's going to be some amount of force needed to hold this object in circular motion, and the force is going to be towards the center. Think about this. Think about taking a string, tying it onto something, and swinging this thing around your head. The forces need to be to the center to keep that happening. So the force then can be set equal to mass times acceleration. Now what I've been suggesting is to think of this as the acceleration, the centripetal acceleration, is a result of some force, and the amount of acceleration will depend on how much force and how much mass. So I want to keep these two formulas separate. What they've done here is they've combined them into one. And I think, especially you guys, you're starting out with, kind of a general physics. Rather than combine the force formula and the kinematics formula right now, I would say keep them separate. And that's what I'm going to try to do with the examples, is look at the kinematics, and then look at the forces, and then once we've looked at them independently, bring those together into a formula. If you start putting together these formulas, packing too much stuff together, it becomes hard to look at the formulas and really remember the steps that got you there. So let's practice looking at the steps. So one of the things that, again, they're pointing out here is, ideally, we can see that the force would have to be inwards. Think about why the forces are inwards for something that's going in a circle, and that the acceleration is also in that direction. So that's one of those conceptual things. This is a good example. The moon orbiting the Earth is a good example. We'll see some more examples as we go along. Okay, so here is what are they calling it here? Oh, they're not telling us. So here's a nice picture here where we've got this metal piece spinning around. We're taking another metal piece and sanding off part of it, and the sparks are flying straight out. So once a piece of metal breaks free, it continues. You can see the bulk of those are going forward. There's a little bit of side velocity on some of the pieces of metal, depending on how they've separated. But this doesn't happen. So there's not a force pulling something outwards. Instead, there's a force pulling stuff inwards. When that force disappears, the object goes in a straight line. All right, here we are. How many times can we spin something around in a circle? And here we go. Tangent is towards the circle. mg is downwards. Now that's kind of interesting. They've got this in a horizontal circle. They say estimate the force a person would need to exert on the string. It's a 150-gram ball, and we want that to go around in a circle with a radius of 60 centimeters. And so it's the same thing, right? It's the same numbers that we looked at before, but now we're going to calculate how much force. So it's still 0.150 kilograms. It's still a radius of 0.60 meters. It is still 2 circumferences every second, and that's 7.5. So those numbers are all the same. This was the acceleration we got in that previous example. The only thing that's different here is that this force, the force calculation, is going to need to be equal to m times a. And so I wrote that as a tension. That looks like a tension force to me. So the F becomes T here. It's 150 grams that needs to be accelerated at 94.7 meters per second. And this is telling me that I'm going to need to have a tension of 14.2 newtons to make that happen. If the tension is not 14.2, then the circular motion won't be maintained. If the string cannot sustain a force, it's only 3 pounds, 3 or 4 pounds here, but if the string is not strong enough, then the string could break and the object would fly off in whatever direction it happens to be traveling at the time the string breaks. Okay, so T is required to keep the object accelerating circularly. All right, here's another circular objects going around in a circle here. This time it's a conical pendulum is what they're calling it. And so what we're doing is using a string. We're using a string here and allowing this thing to kind of swing in this kind of three-dimensionally. And so what we want to think in terms of here, first of all, getting a force diagram set up. So here is a horizontally placed circle. So there's a horizontal circle that this object is going to follow. There's a string attached to this. Now that string is going to provide a tension. And the tension is going to get divided up into 2 components. The tension is going to have a vertical component to it. So here is the vertical component right here. That's force of tension times. Now let's check the angles here. The angle here is theta. But notice that angle is compared to the vertical axis. So this theta would also show up right here. That would also be theta. So this is the cosine theta because it's the adjacent component. Cosine means adjacent. This would be the sine component because it's opposite. So again, angle theta is here. This component is adjacent. This component is opposite. So this is the sine theta. This is cosine. Now they're using the I hat, j hat unit vectors, and that's fine. You don't have to put those in on these diagrams. And then this direction is going to be mg. Oh, one thing I should remember here. Let me go back and take a look. I wanted to clarify this point too. So as far as mg, what about mg in this picture? This is actually the same picture that we're looking at in this example we had started. They're ignoring the effect of mg in this. They're saying that it lowers this by such a small angle that it's not really important. And so they've just said that that's going to be a small amount. They've ignored it. But this time they're not. This time they're saying what happens if this is, a measurable angle. It's a significant angle here, which it is in this example. Well, what that has led to is just some components. So we're just going to have to pay attention to components when we start setting up the force diagrams. So here is that conical pendulum. Here is that angle theta. The direction of acceleration, now this is key, the direction of acceleration is not back along the tension. If I look at the circular motion, where is the center of the circle? And the center of the circle is right there. So that's an essential part of solving these circular motion problems, is finding out where the center of the circle is. And in this case, it takes a little, you have to stop and think about where that center is. Now there's a radius here, there's a radius here. the acceleration will be towards the center, and that means that we need a force to provide that acceleration. So here's my force diagram. I've got an mg, I've got a t cosine theta, and a t sine theta. Which one of those is my centripetal force? Which one is going to provide the centripetal acceleration? And that would be, yeah, t sine theta. So in the vertical direction, I've got t cosine theta equal to mg. In the radial or centripetal, so we sometimes refer to this as the radial direction, same thing as centripetal. That's going to be t sine theta divided by n is equal to the acceleration. I can take those two equations. I can solve for this. T sine theta is equal to m times a. That's right here. And t cosine theta is equal to... So it's our old trick. It's our old trick of taking the two components, t sine theta, t cosine theta, and dividing them so that the t drops out. Notice what also happened here is the m's dropped out. This is a gravitational mass. This is an inertial mass, but they cancel out. So the m's are gone. And that leads us to saying that the acceleration then is given by g tan theta. That's what we're going to have from this equation right here. Now, that's what the acceleration is. I can solve for v squared is equal to r times a. That says that the speed at which this object will be traveling is given by rg tan theta square root. So that's the formula we've come up with. So we've set all the forces equal to the accelerations. And, oh, so it is just, we never did put numbers into that. Right. Okay, so try putting some numbers in yourself, make up some numbers, see what you come up with for that. All right, let's do this. Let's take a look at another important, very important example with friction. And that's, driving an automobile. If I'm going around a curve, and again, back to the very same example, it's easy enough to go in a straight line. Objects tend to go in a straight line all by themselves. They don't need any forces to help them out. But if I'm going to turn this way, I need something to pull me in that direction. So if I get pulled in that direction, I'll turn to the left. If I get pulled to the right, I'll turn to the right. So I'm going to need a force acting on this car to pull the car in that direction. Now, if I'm a passenger in a car, if I'm a passenger in the car, if I'm an object inside the car, anything in the car currently is going in the forward direction. So all of those objects are going to tend to go in the same direction unless a force is acting on them. Now, the car as a whole is depending on what force to enable the car to accelerate to the left or accelerate to the right. And that force would be friction. So it's a frictional force that's going to allow the car to follow the curve of the road. Now for the passenger, they're going to need a force from the seat. Maybe there's a seat belt holding them in place. Typically there's enough frictional force within the car seat, some frictional forces, some normal forces that enable the passenger to follow the path that the car is traveling. All right, here's an example with a racetrack, and you can see how the cars have been coming around the curve, and you can see skid marks. So for the cars where the static friction, when I'm driving a car, I'm using static friction. The tires are not sliding along the surface. So when the tire comes down and makes contact with the surface, it doesn't slip. There's no sliding. It's not kinetic friction, or at least you should not be using kinetic friction when you drive. If you take a test at the DMV, they're going to ask you, which types of friction should you be using in controlling your automobile. And remember, you're always supposed to be using static friction whenever possible. If the road's really slippery and you go and you start to slide, that means you've lost the static friction and now you're depending on kinetic. And that's what these skid marks are. So the car no longer is using static friction where the tires remain motionless relative to the contact point on the road. So instead they've gone into a skid. All right, as long as the tires are not slipping, the friction will be static. That's what we want. If it starts to slip, the friction becomes kinetic, which causes problems for us. First of all, kinetic frictional forces aren't as large. So once you start to slide, it's going to be harder to get back to static friction where you have control of the car. So the kinetic friction forces are smaller, and the kinetic friction forces cannot be used to direct the car. Once the car begins sliding in some direction, friction, kinetic friction works just as well in any direction, and so the car will continue to slide in whatever direction it starts to slide in. With static friction, where we're able to turn the steering wheel and that redirects the static friction, that enables us to have control over what direction the car will travel. All right, this is what the force diagrams are going to look like. Now this is a front view, so we got to be really careful. I'm a little nervous standing in front of that car. So here I am standing in front of the car, but I'm not worried because the car is going to turn to the left, I guess. And so this car is going to be making a left turn. It's not going to hit me. But right as it's coming towards me, I've got a gravitational force that's downwards, mg, and I've got a normal force that's upwards, that's little n. And then here is the frictional force. So the frictional force needs to be, and that's static, I'm planning on this being static friction, that needs to be in the direction that I want to turn. And so the top view, now these two views are really important, so practice drawing the front views, think about where the forces are, and then move on and try drawing the top view. Draw both views, because often in a problem we need both. You could easily be asked in a midterm to draw the front view, show all the forces, draw the top view, front view, draw the top view, show all the forces. Those are important things you should understand, and so you could easily be asked to do that. It says that we're traveling at a certain speed, 54 kilometers per hour. We've got a roadway with a radius of curvature of 50 meters, and it says try this when the road is in good condition and we have a static friction of 0.60. I hope tires have a larger static friction than that. And then also consider a case where it's icy and the static friction is all the way down to 0.25. So here's the top view, here is my side view. From the top view I can see the car's going in that direction, the acceleration is towards the center. I'm going to need a frictional force in that direction. Now here is front views scare me, so I draw back views of the car. Either one's fine. But here is a back view. See, there's the license plate, here are the tail lights here, there's the tires. Those are the treads on the tires. So the velocity is into the page, so I draw velocity vector with a little x to show that. I've got gravity down, normal force up, and who is going to provide the acceleration? Static friction. So static friction is going to come in and provide the acceleration for us. So let's do this. Let's say we're looking at some highway curves, and right at the limit, okay, this is not advised either. Don't always drive right at the limit of your static friction. Give yourself a little margin to work with. But let's say that we're right at the limit of static friction, and that means that we're at mu sub s times n. So this is the static friction that I want to be thinking in terms of. So I'm right at the maximum value. I'm going to divide that through by m. Now, when I write in this expression for the maximum value, the m's cancel out. And it says that the largest acceleration that I can undergo. So what we're doing is we're taking those tires in the pavement right to the limit of static friction. that would say the largest acceleration that the static friction can provide is given by mu sub s times g. That's the limit of my static friction. Now that's looking at forces. Let's take a look at the kinematics. So the kinematics says, what is the acceleration of my car? Well, it's v squared over r is how I can calculate it. That's 15 meters per second squared divided by 50 meters. That was the radius. It's saying that I'm going to need enough friction to maintain an acceleration of 4.50 meters per second squared. That is the acceleration I want my car to undergo. So what we can do then is we can work from these two, well, from this equation and these numbers, and say that mu sub s needs to be at least as large as a over g. Now, the acceleration that I'm undergoing here is 4.50 meters per second squared. The gravitational field is 9.8 meters per second squared. Those cancel out. Remember, the coefficients are unitless. That says that I would need, in order for my car to go around this curve this fast, I would need a static coefficient of at least 0.46. 0.46 is the minimum. So notice how the mass canceled out. I don't need to know the mass of the car for this. I just need to know the conditions of the tire and the pavement, and I need to know what planet I'm on. I'm on Earth, so the gravitational field is 9.80 meters per second squared. And then I need to know the details of how fast and what's the radius. But the mass calculation here, it dropped out. So whichever car, whatever the mass of my car, I'm going to need a coefficient of static friction 0.46. Now what did that tell us? Let's go back. It says that in part A, when the pavement is in good condition, no problem. I'm going to have plenty of static friction there. And I do think that's a low number. I think automobile tires probably go closer to 1 rather than top out at 0.6. What about when the roadway is icy? Nah, when the roadway is icy, I can't do this curve. I don't have enough, I won't have enough friction. If the coefficient drops all the way down to 0.25, I'm going to have to slow down. So the solution here is to slow down so that I don't have, if I slow down and v is smaller, then I won't need as much acceleration. I won't need as much friction force to create that acceleration. Okay, so what about banking? So what we're going to do now is we're going to take the highway, and instead of having the highway be level, what if we bank it? You know, this is what race tracks look like, and highways do too. So you'll see highways occasionally. It's not a lot of banking. This is a pretty steep bank here, but we could also use banking to allow the car to go around the curve at a higher speed, and this is how that would work. By tipping the roadway up. Now remember, this is a front view, so it's not the car going down the incline or coming up the incline. This is the roadway being tipped, which is called banking, and the car now will have a normal force that tips. So the normal force will tip by an angle theta, and that will give us a normal cosine component and a normal sine component. We can use the normal sine component to maintain acceleration for our car. If the roadway is banked here, then if I walk over here and look at, the roadway would be banked over here at the same level. So the center of circular motion is level with the car. The center of circular motion is not here. That would indicate that the car goes up and then it goes down. But as this car goes around in a circle, let me see if I've got my own diagram helps with this at all. It doesn't. So let's talk from here. So the center of the circular motion would be over here. So again, I'm recommending separate out into a force equation and a kinematics equation. They have put both together. I guess it's not a big deal. I mean, this is the acceleration here. But I want to stop and think about this separately. So I'm going to be using a force, a normal force times the sine of theta, the sine theta component, to create the acceleration. That's what this is all saying. So here's an example. So radius of 50 meters. Now it says that the design speed is 50 kilometers per hour. What does that mean? Here is my top view. There is the car's motion, the velocity specifically. Here is the car's acceleration. That's the A for the car. And then here is the back view. I've got a gravitational force downwards. I've got a normal force that's tipped. And as we were saying, what that leads to is an n sine theta, an n cosine theta, mg. Now, n cosine and mg, those are going to be equal because there's no acceleration in that direction. But the n sine theta is going to create the acceleration for us. So for the vertical direction, we can say n cosine theta equals mg. For the centripetal or radial direction, the acceleration is the force divided by mass. N sine theta divided by m. We can use that trick that we just used a little, earlier in the chapter. I can use that to get one formula, n sine theta equals ma. Another formula, n cosine theta equals mg. There they are. I can line those up, cancel out the n's, and look, the m's also go away. And so what that leads to then is, here is the car, here's a back view. The acceleration is horizontal, but it's towards the center. This is theta. This becomes A is equal to G tan theta. Now, the acceleration can be rewritten as v squared divided by r. So that gives us v squared is ra, which is rg tan theta. And it says that the angle of banking, if I take the tangent of that angle, it's going to be equal to v squared over rg. So let's put the numbers in. The radius here was 50 meters. The velocity was 50 kilometers per hour. So I've written that as 50,000 meters per 3,600 seconds. And that gives me a speed of 13.9 meters per second. Putting all the numbers in, I solved for an angle of 1.62. So the idea here is when a curve is designed for a certain speed, we're going to bank the curve. The idea is to bank it in a way where we wouldn't need any friction at all. So if you come back to the force diagram, if you take a look here, what force is missing? There's no frictional force. So in this example, we are using exclusively banking as a way to get around the curve. So we're not using any frictional forces at all. Now, typically when you're driving, if you go around a banked curve, you'd use both. You would be using the banking of the curve, but you would also be using frictional forces. Both effects would be taking place. But in the examples we've been looking at, it looks like we've just been using one or the other. But you could use both. Both could show up. So 1.62 degrees, that's not too extreme. The roadway has been tipped. Just a very small amount is what we're seeing here. Okay, so yeah, so that finishes up what we've got on this one. Okay, so a couple things to keep in mind with circular motion. What we've been looking at so far is uniform circular motion. Uniform circular motion means it's a perfect circle, the r value is fixed, and that we travel at a very steady speed. So v is not changing either. And that's, those are the easiest examples, and those are the ones that we've really concentrated on. Be aware, I'm trying to think, I think there may be one problem in the homework, maybe not, where we're looking at non-uniform circular motion. So in this case, what would happen if, instead of going at a steady speed, what if we started going faster? What if we went faster and faster in these circles? Well, that would say, in addition to the radial component of the acceleration, which is here, I guess, we would also have a tangential. So what's called a tangential. So we would have, in addition to centripetal or radial component, we would have an acceleration along the path that the object is taking. So in that case, I'm not only accelerating sideways, I'm accelerating forward. I'm going faster and faster. Now we could also be slowing down. So it could be that we're going this direction, but we're slowing down, the acceleration is opposite. So anyway, be aware that that's a possibility. Same thing with the forces that we have here, is in order for a radial acceleration, we need a radial force. In order for a tangential acceleration, we need a tangential force. They've drawn these as if it's a combined force, but more often than not, the force providing the radial motion and the force providing the tangential could be viewed as two different forces. All right, here's a path of an object. It's coming in, and it begins to go into these curves. Now, at each point along this curved path, maybe this is a highway that you're driving along, at each point of this curvy path, what we're going to have is radial forces as well as tangential, so both happening at the same time. And any kind of curvy motion can be represented as a combination of radial accelerations and tangential. I don't think we're going to be looking at anything at great detail. This is mostly just something to be aware of, that both can be happening. Now, the other thing that we haven't talked about here, did they point that out? The other thing we have to realize is that r could be changing. The radius is not necessarily fixed either. If you look at a highway curve, if you're driving along, look at a highway curve, the r values vary. So when you're going into a curve, it starts out that the r values are bigger, and then the curve typically becomes a little more tight, and then it relaxes, and then finally goes back to straight line. So we've been treating highway curves as if there's a fixed value of r, and that's not true. Okay, so we've looked at some simplifications for these examples. Okay, the last big topic we want to look at in this chapter, we looked at friction, both static and kinetic. We looked at circular motion, and then we kind of brought those together, and we looked at both. We looked at examples of using frictional forces to maintain circular motion. So what we're looking at now, this last major topic, is that what are called drag forces or resistive forces. These are things like air resistance. So, and that's really the only example that we're going to take a look at here. So here we are. Here's an object. It's got a mass of m. And here is the gravitational force pulling this object down. Now, what we left out back in chapter 2 and whatever, 2 and 3, I guess, with gravitational forces, we left out air resistance. Now, air resistance can be complicated, kind of like friction is complicated. And for air resistance, one of the formulas we could use to kind of model how air resistance works is to say that the air resistance is proportional to the velocity and that it's in the opposite direction. And so that minus sign is reminding us that the direction of the force is opposite to the velocity. Now what that says is when we drop something, here is v as a function of t. And remember, if there's no air resistance, then what happens is the speed just picks up linearly. The speed just gets faster and faster and faster and faster. That's not really what happens to a dropped object. There's what's called a terminal velocity. And terminal velocity occurs when the air resistance force balances out the gravitational force. Now, I think if I remember right, the terminal velocity for just a person, jumping out of a plane with a parachute or whatever, those people, parachutists reach terminal speeds of, what is it, between 50 and 100 meters per second or something, maybe a couple hundred miles an hour. And at that point, the air resistance is so large that they're no longer picking up speed. So they hit, or they asymptotically approach what is called terminal velocity as time goes by. Now, the terminal velocity, I can take this force, the magnitude of this force, and set it equal to the magnitude of this, and say that b times vt is equal to mg. That tells me what the terminal velocity would be for a given object. And since the gravitational force is mg, the b factor, the resistive force constant, has to do with the shape of the object. Is it designed aerodynamically? Is it spread out, or is it more compact? So again, if we use a skydiver, a parachutist as an example, the person themselves has a pretty small value of b. And so since their value of b is relatively small, the air resistance is not extremely large until they reach high speeds. But once the parachute is open, once they release the parachute spreads out, the b value for the parachute is really large. And that means that the terminal velocity with the parachute open is much less. So when they open their parachute, that will slow them down, and they'll approach a new terminal velocity. Now there's an example here, there's a mathematical example I'm going to run through. You guys are not responsible for the details of this, but again, this is one of those examples where if you're interested in more of the details, this is it. So let's say we drop an object with the idea that it's going to have a velocity downwards and that it will have an acceleration downwards. The forces being gravity, and now I'm going to introduce b times v. Now I didn't put the minus sign in here. I'm going to let the diagram show me what direction the minus sign needs to be in. So I'm going to write this as acceleration is mg minus bv. So the minus sign from here is from looking at the diagram, and divide that through by m. Now, if you remember from calculus and from physics, what we looked at here back in chapters 2 and 3, the acceleration can be mathematically represented as the dv dt, the time derivative of velocity. So I've set that equal. And then the next step here would be to take the dt, move it to the right side, take the mg minus bv, move that to the denominator on the left side, and that's what I've done in this step. Once we've got it set up with all of the v's on the left side and all of the t's on the right side, then we can integrate. So at that point, I can carry out the integration. Now, for the integration, we're going to start off at t equals 0, and let's go ahead and say we're going to drop it from rest. So let's say we drop it at rest. It's going to gradually pick up speed as time increases, and the stuff inside the integral signs are telling us how to relate increases in time with increases in velocity. And that depends on the mass of the object, the gravitational field, and what the air resistance coefficient, B, is equal to. So coming back to that diagram we just looked at earlier, what I want to do is simplify some of the formulas that we have here. BV terminal is equal to mg. So when I'm dropping at terminal velocity, these two forces are equal. Well, that enables me to go in and write B times Vt is equal to mg. So the terminal velocity is given by mg over b, same thing we saw before. That enables me to come in and substitute into this equation, and then once we solve for that equation, we end up with a terminal. We're gonna see the details here. We're gonna end up with a formula that says v as a function of time is given by terminal velocity 1 minus e to the minus t over a time constant, which I'm writing as tau. So let's take a look at the details. I think we're at about time right now. Let me take just a couple minutes. For those interested, what we had was a formula that looked like this. I was able to do a substitution into that integral of mg minus bv, and then write down what du would be equal to, and then write down dv in terms of du. So this is a variable substitution, kind of a standard technique in, I guess it's in integration. So it might be second semester calculus rather than first semester. So in any case, making the substitutions into this leaves us with 1 over b, integral 0 to v, du over u. There's a minus sign here we have to put in, 1 over m dt, and then we carry out the integration. So this side integrates out to be the logarithm of u from u to v. The b I brought over to the other side. This becomes minus bm times t. When I evaluate the limits, I'm going to get the logarithm of mg, well actually I unsubstituted. So let's put this back in for u, and when I carry out the limits, what I ended up with was the logarithm of mg minus bv over mg minus 0, because that was the lower limit of the integration. On the right side I got minus b over t, minus b over m times t. Exponentiating, I ended up with mg minus bv over mg is equal to e to the minus b over m times t. So a few lines of algebra here. I brought the mg to this side. I solved for bv. What I'm ending up with here is that v is equal to mg over b times 1 minus e to the minus b over m times t. Now, what we saw was that the terminal velocity is given by mg over b. Now there's what we call a time constant, which tells us how fast we will approach, we're going to asymptotically approach a terminal velocity. How fast does that occur? And that's given by m divided by b. So more m stretches out the process, it makes it take more time, and more b shortens the process. So with these definitions, we can write the velocity as terminal velocity 1 minus e to the minus t. Now, take a look at that equation. Does that work the right way? Let's try this. If I put in t equals 0, this becomes 1 minus 1. That cancels out. So yeah, it actually does work. So this is the stuff in the parentheses is something that shows up very frequently in physics, and that's 1 minus some sort of an exponential. Now you guys, I'm hoping, are familiar with exponentials. 1 minus exponentials look like this. An exponential would be dropping with time, but 1 minus an exponential works the other way. It starts at 0 and asymptotically approaches a final value. Now, the terminal velocity, I think this was for a person. This is something I looked up. So let's say that somebody's parachuting and their terminal velocity is 40 meters per second, like 100 miles an hour or something. the mass is 60 kilograms. This is Earth's gravitational field. And let's say that B then can be calculated as mg over terminal velocity. The B value for that skydiver is 14.7 newtons per meter per second, or about 15. So the tau value, the time constant, m over b, can be calculated to be about 4 seconds. So this is telling us at what rate are we picking up speed. So let's take that 4-second time constant. Now, if I have a formula with 1 minus e to the minus t over tau, over a time constant, that says that after one time constant has gone by, I will have reached 63% of that final asymptotic value. After 2 time constants have gone by, I will be at 84%. After 3 time constants, I'll be at 95. These are just the properties of the exponential function itself. So again, these things show up so commonly in physics. So if I'm a skydiver with these numbers, then after 4 seconds, I will already be at 63% of my terminal velocity. 8 seconds, 12 seconds. At 12 seconds, I'm at 95%. I'm not going to really go much faster. Once I've fallen for, 12, 10, 12 seconds, I'm not going to be picking up speeds to be much higher. Now, again, this is an optional example, but if you're interested, that's something to take a look at. So that finishes up. So we looked at friction very thoroughly. We looked at circular motion. We looked at resistive forces a bit here. And we will stop there. So if you guys have any questions, stop by office hours, chapters 4 and 5. A lot of good stuff in here. A lot of really good examples to work through and think about.